Welcome to Understand the Math. In the video description, you'll find a link to free guided notes that can be downloaded and filled out as you follow along with the video. This video is the first part of a 7-part series on topics that commonly appear on an introductory linear algebra midterm or final exam. In the future, I plan on posting more in-depth linear algebra videos, but I wanted to begin with a short overview series of basic topics. The topics in this first video focus on content related to linear equations. We'll begin by talking about the possible solutions to a linear system with 2 equations and 2 unknowns. Every linear system of equations, regardless of the number of equations or unknowns, has 0, 1, or infinitely many solutions. So there are 3 types of solutions. The following linear systems are examples of each type of solution. Our first example is an example where we have no solution. This means that the 2 equations are 2 parallel lines. Our second linear system is an example where we have 1 solution. And that solution is x is equal to 7/3 and y is equal to 4/3. When we have 1 solution, that means that we have 2 intersecting lines. Our last system of equations is an example where we have infinitely many solutions. This means that we have 2 lines that are the same line. In other words, we have 2 identical lines. Linear algebra is really nice when you can visualize what a solution looks like. When we use matrices to solve a linear system, we'll use either coefficient or augmented matrices. A coefficient matrix is a matrix that contains the coefficients of a linear system of equations. For this linear system of equations, the coefficient matrix looks like this. We have a 1 in front of the x, so we write that here, a -1 in front of the y, and then in the second equation, we have a 2 in front of the x and a 1 in front of the y. And that's our coefficient matrix. An augmented matrix is a matrix that contains both the coefficients of a linear system and the constants from the right-hand side of the equations. For this linear system, the augmented matrix looks like this. We have the coefficient matrix, just like we had above, and then we add on the constants from the right-hand side, which is 1 and 6. It's common to draw a vertical line, and we always call that an artificial vertical line, between the coefficients and the numbers from the right-hand side. And it just helps you visualize that you actually have an equal sign between those 2 sets of numbers. Elementary row operations, echelon and reduced echelon form are used to reduce an augmented matrix. So let's underline that, reduce an augmented matrix to a more simple augmented matrix where we can find the solution to the system pretty easily. If we use elementary row operations on this augmented matrix that's pictured here, we can reduce it to a matrix that looks like this. And in a little bit, I'll go over how to do that, but I just want to explain the structure first. So we have an augmented matrix, we reduce it to a matrix that looks like this, and then from here, we can read off the solution. So this first line tells us, and let's maybe highlight these numbers. So the first line tells us that x1 is equal to 1. The second line tells us that x2 is equal to 2. And the third line tells us that x3 is equal to 3. So that's our goal. We're going to learn how to take an augmented matrix, put it into this form so that we can easily read off the solution. There are 3 elementary row operations that can be used to reduce an augmented or a coefficient matrix to echelon or reduced echelon form. Let's go over these 3 row operations. The first operation that you can do is to multiply a row or an equation by a non-zero constant c. Multiply a row by a non-zero constant c. The second one that you can do is you can interchange 2 rows. And then the third operation that you can do is to add a constant c times 1 row to another row. And I always tell students that 90% of the time, it's this third operation that we're going to use when we're going through a row reduction. Now let's talk about echelon forms. Echelon forms are used with row operations to solve a linear system of equations. There are 2 types of echelon forms. The first type is called row echelon form, and this form is not unique. So let's write that down. What this means is you could have an augmented matrix or a coefficient matrix and you could reduce it and you could get a lot of different row echelon forms. There are 3 requirements for a matrix to be in row echelon form. And we'll often use the term echelon form instead of row echelon form. The first requirement is that all non-zero rows are above any rows of all zeros. So the easiest way to remember this is to remember that this means that you have the 0 rows at the bottom. The next requirement is that each leading entry, which means each first non-zero entry in a row, is in a column to the right of the leading entry of the row above it. So this is easier to think about if you think that this just means that the leading entries are down and to the right. Let's write that down. So the leading entries are down and to the right. The last requirement for echelon form is that all entries in a column below a leading entry are 0. So this is like saying zeros need to be below leading entries. So we'll write down zeros below leading entries. I came up with these phrases as I was trying to teach students how to memorize these 3 requirements. Reduced row echelon form, or just reduced echelon form, is unique. So when you row reduce an augmented or coefficient matrix to reduced echelon form, the form that you end up with will be unique. In other words, there's only one form that you can end up with. There are 5 requirements for a matrix to be in reduced echelon form. The first 3 requirements are the ones in echelon form that we've just gone over, and then there's 2 additional ones. The 4th requirement is that the leading entry in each non-zero row is 1. So let's just write this as leading entries are equal to 1. And then the last requirement is that each leading one is the only non-zero entry in the column. So what that means is that we have zeros above and below each leading entry. I would encourage you to memorize the 3 requirements for echelon form and the 5 requirements for reduced echelon form. Let's now talk about Gaussian elimination and Gauss Jordan elimination. Gaussian elimination involves a 1-part algorithm for reducing a matrix to echelon form. This algorithm consists of what we call a forward phase, and the main goal is to get zeros below the leading entries. And the way that we're going to do this is we're going to work down and to the right. And on the next page, I have an example that will go through this algorithm. So let's write down work down and to the right. Gauss Jordan elimination is a 2-part algorithm for reducing a matrix to row echelon form. So Gaussian elimination, you reduce the matrix to echelon form, whereas with Gauss Jordan elimination, you reduce the matrix to reduced echelon form. So the Gauss Jordan elimination has 2 phases. A forward phase where you get zeros below the leading entries. And we wrote up above, this means we're going to work down and to the right. And then it has a backwards phase where we're going to make the leading entries 1 and get zeros above the leading entries. The way that we're going to do this is we're going to work up and then to the left. So let's write that down. So work up and to the left. We'll now complete an example problem where we'll use elementary row operations, Gaussian elimination, and then Gauss Jordan elimination to solve this linear system of equations. We'll first use Gaussian elimination to solve the system. We'll begin by writing the linear system as an augmented matrix, which I've already done in the notes to get us started. What we need to do is we need to get zeros below our leading entries, and we're going to work down and to the right. So we're going to begin by highlighting our first leading entry. And what we want to do then is we want to get a 0 below the leading entry. The way we're going to do that is we're going to use row operations to make these numbers that I've circled in purple become zeros. So our first row operation is going to look like this. We're always going to work off the row that has the leading entry. So that's row 1. So we're going to take row 2 and we're going to replace it with row 1 plus row 2 because 2 plus -2 is 0. Let's go ahead and let's write that down on our next matrix. So we'll copy down the first row. So we're going to add row 1 to row 2. So 2 plus -2 is a 0. 2 plus 5 is 7. 2 plus 2 is 4. And then 0 plus 1 is 1. Now we're going to get a 0 in the third row. So we're going to replace row 3 with -4 row 1 plus row 3. So that will give us -4 times 2 is 8. I'm sorry, -8 plus 8 gives us a 0. So let's write that down. -4 times 2 is -8 plus 8 is a 0. -4 times 2 is -8 plus 1 gives us a -7. And then -4 times 2 gives us a -8 plus 4 gives us a -4. -4 times 0 is just 0. So the -1 just comes along for the ride. Now what we're going to do is we're going to work to the right. So we went down. Now we're going to go to the right. And we're going to focus on our next leading entry, which is 7. So what we need to do is to get a 0 below this leading entry. So that means we're going to take row 3 and we're going to replace it by row 2 plus row 3. So let's copy down over here our matrix 2, 2, 2, 0, 0, 7, 4, 1. Now we can work on row 3. So we're taking row 2, adding it to row 3, and that's what our row 3 is going to be. So 7 minus 7 is 0. So we have a 0, 0. 4 minus 4 is 0. 1 minus 1 is 0. Great. So our leading entries are down and to the right. We have zeros below each leading entry, and our row of zeros is at the bottom. We don't always have a row of zeros, but if we do, it has to be at the bottom. Now we're going to begin the algebraic portion of using Gaussian elimination to solve this linear system. What we're going to do first is we're going to take our augmented matrix and write it in algebraic form. So our first equation is going to be 2x1 plus 2x2 plus 2x3 is equal to 0. And our second equation is going to be 7x2 plus 4x3 is equal to 1. We're going to solve this by solving the second equation first and then the first equation. So let's notice that x2 is connected to that leading entry. So that tells us that we need to solve for x2 and not for x3. That gives us 7x2 is equal to 1 minus 4x3. So x2 is 1/7 minus 4/7 x3. Notice that there is no leading entry in the third row. So that means that x3 is what we call a free variable or a parameter. It's very common to replace free variables with a different letter that are more commonly used as parameters. So we're going to let x3 be equal to t and then solve for x2. So x2 is then 1/7 minus 4/7 x3, which we now replaced with t. We're now going to solve for x1. So let's just note the connection between x1 and our leading entry in the first row. That tells us that we're solving for x1. So let's do that. So x1 is equal to minus x2 minus x3. We'll then plug in what we got for x2 and x3. So minus, and in the parentheses, we plug in x2, 1/7 minus 4/7 t minus x3, which is t. And then we need to do a little algebra to get that all combined. So we have minus 1/7, and then we have a 4/7 minus 1. So that's 4/7 minus 7/7 gives us a minus 3/7 t. Great. So it's common when you write down the solution for one of these problems to write it down in a really orderly manner. So we're going to start with x1. So x1 is going to be minus 1/7 minus 3/7 t. x2 is going to be 1/7 minus 4/7 t. And then x3 is going to be equal to t. So this is the solution using Gaussian elimination. So Gaussian elimination is really a combination of row reduction and some algebra. What we ended up with a solution is infinitely many solutions because t can take on any value between minus infinity and infinity. So this is an example of a linear system with infinitely many solutions. We're now going to use Gauss Jordan elimination to solve our linear system. What I'm going to do is I'm going to fill in the two blank matrices on the top with what we got from the last page. So that looks like this. So we have a 2, 2, 2, 0. We had a 0, 7, 4, 1, a 0, minus 7, minus 4, minus 1. And then we had a 2, 2, 2, 0, 0, 7, 4, 1. And then lastly, a row of zeros. So this matrix that I just finished writing is in echelon form. Gauss Jordan elimination does not have an algebraic component to it. So what it does is it takes a matrix, it goes through the forward phase. Let's go ahead and write down this is what we call the forward phase, where we worked down and to the right. Now we're going to do what we call the backwards phase, where we're going to work up and to the left. To begin the backward phase, we're going to work on the second row, and I'm going to highlight the leading entry in the second row. So the two requirements for reduced echelon form that are in addition to echelon form is that our leading entries need to be 1, and we need to have a 0 above our leading entries. So let's begin by making that leading entry of 7 equal to 1. So the way that we'll do that is we're going to take row 2 and we're going to replace it with row 2 divided by 7. So let's go ahead and let's write that down. Remember, with the backwards phase, we work from the bottom to the top. So I'm going to write down the bottom row of zeros first. Then we'll replace our second row with our second row divided by 7. So 7 divided by 7 is 1. And then we have 4 divided by 7, and then 1 divided by 7. And then we'll recopy above it our top row. Now what we're going to do, highlight our leading entry again, which is 1 now, which is great. And we want to get a 0 above that leading entry. So we're going to work off of the second row and change the first row. So we're going to have row 1 becomes row 1 minus 2 row 2. And that'll turn that 2 into a 0. So we'll copy down our bottom row, then we'll copy down our second row, and then we'll find our new first row. So the 2 stays the same. And we have minus 2 times 1 is minus 2 plus 2 is 0. Minus 2 times 4 over 7 is minus 8 over 7. 8 over 7 plus 2. So that's minus 8 over 7 plus 14 over 7, which gives us a 6 over 7. Never be afraid to write down your arithmetic in the margins. It really helps not having to keep everything in your head. Then for our last one, we have minus 2 times 1/7 plus 0 gives us a minus 2/7. We're almost done. We're going to highlight our leading entry. We have to get that leading entry equal to 1. So what we're going to do is we're going to take row 1 and we're going to replace it with row 1 divided by 2. So that gives us a bottom row of zeros. I almost forgot to write those rows first. 0, 1, 4/7, 1/7, and then here we go. We're going to take the top row, divide it by 2. So we have a 1, 0. We get a 3 over 7 because 6 divided by 2 is 3, and then a minus 1 over 7. Now we're pretty much done. We are going to now solve just like we did with Gaussian elimination. We're going to solve for our leading variables. So this gives us x1 plus 3/7 x3 is minus 1/7. And then x2 plus 4/7 x3 is 1/7. Let's now make a note that x3 is equal to t, just like we did on the previous page. So we can now solve for x1. So x1 is minus 1/7 minus 3/7 t. x2 is 1/7 minus 4/7 t. And lastly, x3 is equal to t. I always tell my students that once you get used to doing this, you don't need to write down that part that I just circled. You'll be able to go straight from the last matrix to this solution. Let's now talk about consistent and inconsistent linear systems. A consistent linear system is a system of equations with one or infinitely many solutions. An inconsistent system is a system of equations with no solutions. Let's kind of outline this in a bit of a flow chart. So let's say we have a linear system. We learned previously that it can have 3 solutions. So no solution, 1 solution, or infinitely many solutions. So if it has 1 or infinitely many solutions, it's consistent. And if it has no solutions, it's inconsistent. Let's now complete an example where we need to find the values of a parameter k for which the linear system of equations is consistent. That's going to help us really understand these two definitions a little bit better. So the procedure of what we're going to do is we're going to take the system and we're going to put it in an augmented matrix. And then we're going to put it in echelon form. Echelon form is used to determine if we have a solution, and then if we ever want to find what the solution actually is, we have to put the system in reduced echelon form. So let's go ahead and let's start this. We'll put this in an augmented matrix. So 1, 2, K4, minus 2, 1. We're going to start with our leading entry, and we're going to get a 0 below that leading entry. So row 2 is going to be replaced with minus 2 row 1 plus row 2. So let's do that. So we'll write down row 1 first, and then we'll change row 2. So minus 2 times 1 is minus 2, plus 2 gives us a 0. Minus 2 times k is minus 2k. So this is 4 minus 2k. And then minus 2 times minus 2 is 4, plus 1 is 5. Now we're going to focus on this term right here. If 4 minus 2k is equal to 0, we would have 0x1 plus 0x2 is equal to 5, which is 0 is equal to 5, which can't happen. This would be an example of no solution. Our problem asks to find the values of k for which we have a consistent system. In other words, for which we have a solution. So what we're going to do is we're going to have to require that we don't have no solution. I always tell my students that's kind of like thinking backwards. So that is going to tell us that 4 minus 2k cannot be equal to 0, or 4 is not equal to 2k, or k is not equal to 2. So our system is going to be consistent if k is all values not equal to 2. And let's go ahead and let's box that. So in practice, when you have to determine what will make a system consistent, it's often easier to think about what would make it not consistent, or in other words, what would make it inconsistent. The next topics I'll talk about are linear combinations and span, and these two go really well together. We'll begin with the topic of linear combination. We say that W is a linear combination of the vectors v1, v2, all the way up to vr if W can be written like this. W is equal to k1 v1 plus k2 v2 plus ... plus kr vr. So whenever you do a problem where you're working with a linear combination, this is the equation that you need to start with. This equation is going to have a solution for our k values if W is a linear combination of the v's. If W is not a linear combination of the v's, we won't have a solution. We're now going to look at a problem where we're going to have to determine if W is a linear combination of two vectors v1 and v2. And if it is, we're going to go a step further and we're going to state the linear combination. So the way we're going to begin is we're going to use that equation that says W is a linear combination of V1 and V2. So we'll start with W equal to K1 V1 plus K2 V2. And we're going to ask ourselves, does this have a solution? So what we're going to do is we're going to take our augmented matrix V1, V2, augmented with W, and we're going to reduce it to echelon form. Because echelon form is the form that tells us if we have a solution or not. So let's go ahead and let's do that. We'll write down the linear system first. And then once you get used to doing this, you won't have to do this step. So we have 9 is equal to K1 times 1 plus 6K2. So let me just highlight what we did here. So we took this, and that. Then the next one, we're going to take the 2, and the 4. And that's going to give us 2 is equal to 2K1 plus 4K2. Next, we're going to take the blue numbers, and that gives us 7 is equal to minus K1 plus 2K2. Now we're prepared to write down our augmented matrix. So that's going to look like 1, 2 minus 1, 6, 4, 2, augmented with 9, 2, 7. And we're going to put it in echelon form. I am not going to go over the in-between steps to put it in echelon form. We just went over that previously. So I'm just going to make some dots. Nothing mathematical. That's just me saying, hey, we're going to skip some steps. So what we end up with is 1, 6, 9, 0, 1, 2. And remember, our echelon form is not unique, so if you stopped the video and did this on your own, you might have gotten a little bit different of a form than I did. So let's highlight now our 2 leading entries. So we have a leading entry in each column. Let's write that down. So we have a leading entry in each column. Therefore, we have a solution. So our solution exists, and that tells us that W is a linear combination of V1 and V2. Now we're going to go one step further, and we're going to find out, what does that linear combination look like? Like if we wanted to represent vector W in terms of vector V1 and V2, how would we do that? So what we're going to do is we're going to now put the matrix in reduced echelon form. So let's go ahead and let's do that. What we would end up doing is multiplying row 2 by minus 6, adding it to row 1, and here's what we're going to get. We have a 0, 1, 2, and then we would have a 1, 0, minus 3. Now let's go ahead and let's solve that. Let's remember that we are solving for K1 and K2. If we highlight our leading entries, The first one will give us K1. So K1 is minus 3. K2 is equal to 2. We can say then that W is equal to K1 or minus 3 V1 plus 2 V2. And you can glance back up at the vectors and you can verify that that's actually the solution. There's a lot of really cool built-in linear algebra checks that you can do, which makes it great. Let's now talk about the span of a set of vectors. So the span of a set of vectors is written like this. The span of V1 to VR. It is the set of all linear combinations of V1 through VR. So that's a good definition to memorize. So mathematically, we would say the span of V1 to VR, instead of saying in words all linear combinations, we would write that it's K1 V1 plus K2 V2 plus dot 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 plus KR VR. Now let's look at two examples. Our first example says, does the set of vectors 1, 1, minus 1, 2 span R2? So what is that really asking? I feel like linear algebra, you spend half the time trying to figure out what are they actually asking. Once you figure that out, it's not hard to do the math. So what this means is there a vector B, and we'll call this B1, B2, where B is equal to K1 times 1, 1 plus K2 times minus 1, 2. Because if this set of vectors spans R2, then any vector in R2, which we're representing by vector B, can be written as a linear combination of those two vectors. Where we're going to go from here is we're going to put this system of equations in an augmented matrix and then reduce it to echelon form to see if we have a solution. So here we go. So we're going to put our matrix, so 1, 1, minus 1, 2, and B is B1, B2. And we're going to put this in echelon form. So we actually only have to change one row, so we're going to do row 2 goes to row 2 minus row 1, because we're working off of that row. So this gives us 1 minus 1 B1. Now we have to think. So we're going to multiply the top row by minus 1, add it to the next row. So we get a 0, and then we're going to get a 3, and then a B2 minus B1. We have a leading entry in each column, so that means we do have a solution. So this tells us that no matter what B1 and B2 are, we are always going to have a solution. We'll write that down. This has a solution for all B, and that tells us that our answer is yes. This set of vectors spans R2. In our last example, we're asked for what value of H is B in the plane spanned by A1 and A2. So in other words, instead of saying, is B in the span of A1 and A2, we're having to find out what particular B, in other words, what particular value of H will enable B to be in the plane spanned by A1 and A2. So same type of analysis, we're going to be able to figure out for what value of H does K1A1 plus K2A2 equal to B have a solution. So our procedure is we're going to take A1, A2, augment it with B, and put it in echelon form. So let's first create that augmented matrix. So 1, 4, minus 2, minus 2, minus 3, 7, augmented with 4, 1, H. And then we'll put this in echelon form. I'm going to skip those steps. And what we end up with looks like this. 1 minus 2, 4. If you need extra practice in row reduction, I would suggest that you stop the video and do the row reduction yourself and see if you get the same thing. And again, you might not get exactly the same thing because it's not unique, but you will end up with the same answer. In order to have a solution, we can't have 0 is equal to a non-zero number. So that's going to require us to state that H plus 17 has to be equal to 0. It can't be equal to a number other than 0 because that would lead to no solution. So this gives us H is equal to minus 17. We went over a lot of material, so I would suggest that you look over the notes to review these concepts and redo any of the problems that you feel like you need more practice on.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.